In this lesson, we will discuss agglomerative clustering. We will go over the agglomerative nesting algorithm AGNES and examine how different cluster linkage methods are going to determine which points then clusters to be merged. The AGNES algorithm continuously merges nodes that are least dissimilar or most similar based on a distance or a similarity measure. Eventually, all the nodes are going to belong to the same cluster. However, the final clustering is going to depend on which cluster linkage method was used in the merging process. Next, we will go over a number of cluster linkage methods. The first method is the single link, also known as the nearest neighbor approach. In this method, the distance between two clusters is defined as the distance between their closest pair of points. So if we have 1 point from cluster A and 1 point from cluster B that are very close to each other, that distance becomes the representative distance between the two clusters. To compute it in practice, we take every pair of points across the two clusters, compute their distances, and then select the smallest one. That smallest value is what we call the single link distance between the clusters. Now, one might say that feels a little bit arbitrary. Why should we consider the nearest pair? A natural alternative is to do just the opposite, to define the distance between the two clusters based on the farthest points, which bring us to the complete link method, also known as the farthest neighbor or diameter-based approach. In this case, we again consider all possible point pairs across the two clusters, but this time we take the largest distance. The intuition here that if even the most distant pair between the two clusters is fairly close, then the cluster themselves must be compact and well defined. So in single link, we merge clusters based on their closest connection, which can lead to chain-shaped clusters, whereas in the complete link, we merge clusters that minimize the maximum pairwise distance. Note how in both cases, the single link and the complete link, these methods are sensitive to outliers. Next is the average link. The distance is defined as the average distance between every pair of points, one from each clusters. So we compute all pairwise distances between these two clusters and then take the average. This seems a compromise between the single link, which uses the minimum, and the complete link, which uses the maximum. However, it's expensive to compute. Let's say we have N1 points in cluster 1, N2 points in cluster 2, so we need to do N1 by N2 distance computations. On the other hand, the centroid link defines the distance as the distance between the centroids. So instead of computing all pairwise distances as in the single link, complete link, and average link methods, we just compute the mean of each cluster and then the distance between these two means, which makes it faster to compute, but it also assumes that the clusters are spherical in shape. The group averaged agglomerative clustering extends this idea. Suppose we merge two clusters, cluster A and cluster B, into one cluster. The new centroid can be computed very efficiently without having to directly perform all of these pairwise distances by multiplying the number of points in the first cluster by its centroid plus the number of points in the second cluster by its centroid, then divide by the total number of points. So this is a similarity measure which estimates the average of their distances without having to directly compute these distances. Finally, Ward's criterion measures how much the sum of squared errors increases when two clusters are merged. So every time we merge clusters, the total SSE will go up. So Word's idea is to merge clusters that cause the smallest increase in SSE. Mathematically, it's given by this formula, which keeps clustering tight and compact as we merge. So to summarize, average link is balanced but expensive. Centroid link is faster but makes assumptions about the shape. The group average agglomerative clustering formalizes an efficient way to compute the average. And Word's criterion provides a principled way to merge clusters that minimally increase the total error. Let's walk through an example to understand how agglomerative clustering works. We have 5 two-dimensional data points. Their pairwise distances are shown in a distance matrix. Searching through the matrix, we find that the smallest distance between any two data points is 2.2, which is between A and B. So we merge A and B into one cluster. Next, we recompute the distance matrix. Remember that under the single link method, the distance between two clusters is defined as the minimum of all pairwise distances. How this plays out, the distance between A and B is the minimum between the distances between AC and BC. We do the same for D and E to get the remaining distances. Next, we identify 3.2 as the smallest distance, which is between D and E. We merge D and E together into one cluster, recompute the distance matrix. For example, the distance between DE and AB is the minimum distance between DAB, EAB. Similarly, we compute the distance between DE and C. Next, we find that 4 is the next smallest value. We group AB and C together, recompute the distances. Notice how the minimum distance between DE and ABC is computed as the minimum distance between DEAB, DE, and C. Finally, we merge everything into a single cluster, ABCDE. The dendrogram now shows all merges in hierarchical order from individual points all the way to one cluster. In summary, the example demonstrated the idea of agglomerative clustering. We don't need to specify K in advance, but in some way we get a full hierarchy of clusters for all possible Ks if we pay attention to the dendrogram. In other words, once the dendrogram is constructed, we can simply cut it at any level to obtain the desired number of clusters. Let's now look at how everything plays out when we compare the 4 main linkage methods across 5 datasets with different shapes. Starting from the bottom, this dataset is what one might call the k-means dataset. It has 3 nicely separated, roughly spherical clusters, and all of these linkage methods are going to do just fine because these clusters are cleanly separated and globular. In such case, just pick the least expensive method. Back to the top row, here we have concentric circular clusters. Interestingly, the single link performs very well because it's dictated by minimum distances between the clusters. Average link, on the other hand, struggles badly. Remember, average link implicitly assumes that each cluster can be represented by its centroid. So as soon as one makes such an assumption, they are leaning towards spherical clusters, so average link fails as expected. Complete link also does not perform very well because it focuses on the farthest points between the clusters, which can distort the grouping in this circular structure. Word link, which also relies on the centroid and variance ideas, perform similarly poorly. The second dataset is the classic 2 moons problem. This one is challenging, but not as extreme as the concentric circles. Single link, again, performs reasonably well. It can follow the curved shape of each moon. Average link and word link both try to enforce globular structure, so they cut across the moons and perform poorly. Complete link does somewhat slightly better here since it avoids the chaining effect and can maintain tighter, more separated clusters. The middle datasets are noisy and contain stretched clusters. Single link begins to fail because it's very sensitive to noise. It tends to chain through scattered points, connecting clusters that should not be merged. An interesting fact about this dataset, it ended up clustering one point here. If you zoom, it's gonna be in green into its own cluster and all other data points in one cluster. Average link and complete link both do better in this setup because they average across points and don't rely entirely on minimum distance. Word link generally performs the best when noise is present because it minimizes the total variance within the clusters. To summarize, each linkage method has its strengths and weaknesses, and there is no universally best choice. It's always going to depend on the shape and the noise level of the data. In summary, we discussed hierarchical clustering and covered a number of linkage methods.